Here's video help for problem 28.3. Actually, here the homework advice, the written out is fine. It is addressed to exactly the right problem. There hasn't been a revision of that. What we're doing here is using the SMASH method. We're measuring the signal from 3 different coils, and we're going to talk about where those coils are and how we should arrange them. By the way, we're always talking about real B field here, that's script B. So that's the X component. Remember, our complex convention is the real part is the X component. We can look at a situation where the Y component is small. So the first thing we want to do is, what are the profiles? Well, how does this look? What's this function look like? What's its Y dependence? If we had a big giant coil here, the magnetic field has this generally strong upward direction in the center, and then of course it gets weaker and starts bending out like a donut on the edges. So the X component going right along the X equals 0 axis looks a bit like this. We die off, the X component dies off as we get toward the edges, but it's kind of uniform, smooth in the center. Well, actually, you know what we could do? We could take 3 coils. In fact, maybe one way we just address this problem is, imagine we're going to instead have 3 small coils or smaller coils, and if we had them arranged so that they're connected like this, so then the currents would flow like this. By the way, you may remember I should equal 1, and so I don't care which direction it's going in. And it's this unit current reciprocity result. But if I connect this way, whatever currents do flow, they're going to flow like that, if I've got it connected that way. And we'd have something that looks a bit like that. Well, not so, constant in the middle, but, roughly so. There's also the butterfly. If I actually, flip it over, so then the currents are opposite as far as the currents closest to us. Well, then this magnetic field, if I say the current's going in this direction, I've got kind of a peak here, goes through 0, and then a negative peak. Or let's say we have 3 coils and we connected them like the butterfly at each juncture. Then it would sort of look like this. The X component along the X equals 0 line, the Y dependence. So if you had 3 coils and you could then pick up the data any way you wanted, and I suppose for this purpose of this problem is just imagine you could freely take data with this arrangement, and then take data with this arrangement, and then take data with this arrangement. How would that correspond to the sinusoidal field profiles that we'd like to simulate? In part B, we're going to assume we do it, and we're going to take some weight, some combination of these signals. So that would really correspond, the combination of the B's. So if I replace this beta by this sum, then of course I get a sum of those signals. And if this were a perfect phase factor for P equals 0 and 1, it's delta K, and you were able to arrange, one of the coils, say, one set of coils to give you a nice cosine profile, another to give a sine profile, and a third to kind of give a roughly constant. Then if you could do this, and you could put, just stick those things in, put those functions right in for beta, can you find some weights that give you that for P equals 0 and 1? You then have essentially 3 equations, because for P equals 0, you're going to get 1 equation. For P equal 1, you're going to get 2 equations, because the cosines and the sines have to separately cancel on both sides of the equation. So you get 3 equations, perfect. Your 3 unknowns, your 3 weights. And there's some more comments about that in the written. Well, the p equals 0 result corresponds to what you measured. Now, given that, if you've got these other coils that you can fill in, if you've sort of simultaneously made measurements this way, then at p equal 1 you can just fill in the odd by using this weight, this combination of weights of your coils. And that's the way you save time with SMASH, because you've done this all at once and you've saved half of the gradient time this way.